According to National Electrical Code Section 250.66, the grounding electrode conductor, or GEC, must be sized based on the calculated fault current at the building or structure. Since you are replacing the service laterals, a fault current calculation should be performed to determine the required GEC size. National Electrical Code Section 250.106 allows supplementing the grounding system of a building or structure by bonding to other grounding systems, such as a metal underground water pipe or building steel. The number 2 solid copper ring around the site may not meet the requirements for grounding. It is not 30 inches deep and it may not be a continuous loop. Since the copper ring does not meet the requirements for grounding, it is not advisable to bond to it as a supplementary grounding electrode. Instead, a proper grounding electrode system should be installed per National Electrical Code Section 250.52, such as firstly, a minimum of 2 8-foot ground rods driven at least 6 feet apart, secondly, a buried metal plate or grid, or thirdly, a concrete encased electrode. Once a proper grounding electrode system has been installed, it can be bonded to the existing number 2 copper ring for additional lightning protection. To summarize, firstly, size the grounding electrode conductor based on fault current calculations per National Electrical Code Section 250.66. Secondly, do not bond to the existing number 2 copper ring as a supplementary grounding electrode. Thirdly, install a proper grounding electrode system per National Electrical Code Section 250.52. Fourthly, consider bonding the new grounding electrode system to the number 2 copper ring for lightning protection. Calculating fault current is crucial for proper grounding. The fault current calculation determines the maximum amount of current that could flow during a fault condition. This value directly impacts the required size of the grounding electrode conductor. Using a grounding electrode conductor that is too small can lead to overheating and potentially dangerous conditions. Several factors influence the fault current calculation, including the available fault current from the utility, the impedance of the service transformer, and the length and size of the service conductors. Various software programs and online calculators can assist in performing fault current calculations. However, it is important to understand the underlying principles and input the correct data to ensure accurate results. When selecting a grounding electrode system, consider the soil conditions. Soil resistivity plays a significant role in the effectiveness of a grounding electrode. Low soil resistivity allows for better current dissipation. If the soil resistivity is high, multiple ground rods or other grounding electrodes may be necessary to achieve the required grounding resistance. The spacing between ground rods is also important. As mentioned earlier, the ground rods should be at least 6 feet apart. Closer spacing can reduce the effectiveness of each individual ground rod. Proper installation of ground rods is also critical. The ground rod should be driven vertically into the ground until at least 8 feet of the rod is in contact with the soil. If bedrock is encountered, the ground rods can be buried horizontally in a trench at least 30 inches deep. For concrete encased electrodes, the electrode should consist of at least 20 feet of bare copper conductor with a minimum size of number 4 American wire gauge. The conductor should be encased in at least 2 inches of concrete and located within the bottom portion of a concrete foundation or footing that is in direct contact with the earth. A buried metal plate electrode should have a surface area of at least 2 square feet. The plate should be buried at least 30 inches below the surface of the earth. When bonding the new grounding electrode system to the existing number 2 copper ring for lightning protection, use a bonding jumper of appropriate size. The bonding jumper should be sized according to National Electrical Code Section 250.66, based on the size of the largest ungrounded service conductor. Ensure that the bonding connections are made using approved connectors and that the connections are mechanically sound and corrosion resistant. Proper grounding and bonding are essential for electrical safety and equipment protection. By following the guidelines outlined in the National Electrical Code and best practices, a safe and effective grounding system can be achieved. Remember to consult with a qualified electrical professional for specific guidance on grounding requirements for any particular application. It is important to understand the difference between grounding and bonding. Grounding provides a path for fault current to return to the source, allowing overcurrent protective devices to operate and clear the fault. Bonding connects non-current carrying metal parts together to create an equipotential plane, minimizing voltage differences and reducing the risk of electric shock. The grounding electrode conductor connects the grounded service conductor to the grounding electrode system. The equipment grounding conductor connects the non-current carrying metal parts of electrical equipment to the grounding system. Both grounding and bonding are crucial for electrical safety. Regular inspection and maintenance of grounding systems are important. Check for loose connections, corrosion, and damage to grounding electrodes and conductors. Periodically test the grounding resistance to ensure that it is within acceptable limits. If the grounding resistance is too high, additional grounding electrodes may be necessary. The National Electrical Code provides comprehensive requirements for grounding and bonding. It is important to stay up to date with the latest edition of the National Electrical Code and to follow its guidelines carefully. In addition to the National Electrical Code, local codes and regulations may also apply. Be sure to check with the local electrical inspector for specific requirements in the area. Proper grounding and bonding are not only essential for electrical safety, but also for the proper operation of sensitive electronic equipment. A well-designed grounding system can minimize electrical noise and interference, improving the performance and reliability of electronic devices. Grounding and bonding requirements can vary depending on the type of building or structure. For example, hospitals and other healthcare facilities have more stringent grounding requirements due to the sensitive electronic equipment used in these facilities. Industrial facilities also have unique grounding challenges due to the presence of heavy machinery and equipment. Proper grounding and bonding are essential for protecting electrical equipment from damage caused by lightning strikes. A lightning protection system should be installed in accordance with the National Fire Protection Association Standard 780. The lightning protection system should be properly grounded to provide a path for lightning current to flow to ground. Surge protective devices, or SPDs, can also help protect electrical equipment from voltage surges caused by lightning or other events. SPD should be installed at the service entrance and at branch panels to provide comprehensive surge protection. When working on electrical systems, always follow safe work practices. Energize the circuit before working on it. Use appropriate personal protective equipment, such as gloves and safety glasses. And never work alone. Proper grounding and bonding are not just a matter of code compliance. They are essential for protecting people and property from electrical hazards. By understanding the principles of grounding and bonding and following the guidelines outlined in the National Electrical Code, a safe and reliable electrical system can be achieved. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. Table 250.66 in the National Electrical Code provides guidance on selecting the appropriate size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding electrode conductor can be made of copper, aluminum, or copper-clad aluminum. The type of material used for the grounding electrode conductor should be compatible with the other materials in the grounding system. The grounding electrode conductor should be installed in a protected location where it is not subject to physical damage. The grounding electrode conductor should be connected to the grounding electrode using an approved connector. The connection should be made in a way that ensures a permanent and reliable electrical connection. The grounding electrode system should be tested periodically to ensure that it is functioning properly. The test should be performed by a qualified electrician. The results of the test should be documented and kept on file. If the grounding electrode system is not functioning properly, it should be repaired or replaced. A properly functioning grounding electrode system is essential for electrical safety. The National Electrical Code requires that all electrical systems be properly grounded. Grounding provides a path for fault current to return to the source, which helps to protect people from electric shock. Grounding also helps to protect electrical equipment from damage caused by overvoltages. Overvoltages can be caused by lightning, switching surges, or other events. A properly grounded electrical system will help to protect people and equipment from these hazards. It is important to note that grounding is not the same as bonding. Grounding provides a path for fault current to return to the source, while bonding connects non-current carrying metal parts together to create an equipotential plane. Both grounding and bonding are important for electrical safety. The National Electrical Code provides detailed requirements for grounding and bonding. It is important to follow these requirements carefully to ensure that the electrical system is safe and reliable. If there are any questions about grounding or bonding, consult with a qualified electrician. A qualified electrician can help to ensure that the electrical system is properly grounded and bonded. Proper grounding and bonding are essential for electrical safety. Do not take shortcuts or cut corners when it comes to grounding and bonding. A properly grounded and bonded electrical system will help to protect people and equipment from electrical hazards. Regular maintenance of the grounding and bonding system is also important. Check for loose connections, corrosion, and damage to the grounding electrodes and conductors. If any problems are found, they should be corrected immediately. A well-maintained grounding and bonding system will help to ensure that the electrical system remains safe and reliable for many years to come. The information provided in this narration is for general informational purposes only and should not be considered as professional advice. Always consult with a qualified electrical professional for specific guidance on grounding and bonding requirements for any particular application. Neglecting proper grounding techniques can lead to severe consequences, including electrical shocks, fires, and equipment damage. A grounding system serves as a crucial safety net, diverting dangerous fault currents away from individuals and sensitive electronics. When a fault occurs, such as a short circuit, the grounding system provides a low resistance path for the current to flow back to the source. This allows the overcurrent protection devices, like circuit breakers or fuses, to quickly trip and interrupt the flow of electricity, preventing potential harm. Without a proper grounding system, fault currents can find unintended paths, such as through a person touching a faulty appliance or through the building's metal structure. This can result in severe electrical shocks or even electrocution. Furthermore, inadequate grounding can cause equipment damage by allowing voltage surges and electrical noise to propagate through the system. Sensitive electronic devices, such as computers and medical equipment, are particularly vulnerable to these disturbances. A well-designed grounding system minimizes these risks, ensuring the safe and reliable operation of electrical equipment. The selection of appropriate grounding electrodes is critical for effective grounding. Ground rods are a common choice, but other options include ground plates, underground metallic water pipes, and concrete encased electrodes, also known as UFA grounds. The choice depends on factors such as soil conditions, available space, and local regulations. Soil resistivity is a key factor to consider. High soil resistivity hinders the flow of current, making it more difficult to achieve a low resistance ground. In such cases, multiple ground rods or chemical ground rods may be necessary to improve grounding effectiveness. The depth and spacing of ground rods also play a role. Deeper rods generally provide better grounding, as they reach more stable soil conditions. Proper spacing between rods is essential to avoid overlapping of their effective grounding zones. The National Electrical Code provides specific guidelines for grounding electrode installation, including minimum depths, spacing requirements, and acceptable grounding electrode types. Adhering to these guidelines is crucial for ensuring a safe and compliant electrical system. Regular inspection and testing of grounding systems are essential to verify their effectiveness. Ground resistance testing measures the resistance of the grounding system to earth. High resistance indicates a poor ground connection, which can compromise safety. Visual inspections can identify loose connections, corrosion, and physical damage to grounding electrodes and conductors. Any identified issues should be promptly addressed to maintain the integrity of the grounding system. Grounding and bonding are distinct but complementary concepts. Grounding provides a path for fault current to return to the source, while bonding connects non-current carrying metal parts to create an equipotential plane. Bonding minimizes voltage differences between metal parts, reducing the risk of electric shock. All metal enclosures, conduit, and equipment frames should be properly bonded together and connected to the grounding system. This ensures that if a fault occurs, the current will flow safely back to the source without posing a shock hazard. The size of grounding and bonding conductors is determined by the size of the service entrance conductors or the rating of the overcurrent protection device. The National Electrical Code provides tables and guidelines for selecting the appropriate conductor sizes. Using undersized conductors can compromise the effectiveness of the grounding and bonding system. Proper installation techniques are essential for ensuring reliable grounding and bonding connections. Connections should be made using approved connectors and fittings. Surfaces should be clean and free of corrosion. Connections should be mechanically secure and electrically conductive. Torque specifications should be followed when tightening connections to ensure proper contact pressure. The use of antioxidant compounds can prevent corrosion at connections, especially when dissimilar metals are involved. It is important to understand the role of the equipment grounding conductor, or EG. The equipment grounding conductor provides a low impedance path for fault current to return to the source from non-current carrying metal parts. The equipment grounding conductor can be a wire, a metal conduit, or other approved means. It should be properly sized and connected to all metal enclosures, equipment frames, and other non-current carrying metal parts. The equipment grounding conductor is essential for ensuring that overcurrent protection devices will quickly trip in the event of a fault. Isolation transformers are used in some applications to isolate electrical equipment from the grounding system. Isolation transformers provide a high impedance path for ground currents, reducing the risk of ground loops and electrical noise. However, isolation transformers do not eliminate the need for grounding. The secondary side of the isolation transformer must still be properly grounded. Static electricity can accumulate on non-conductive surfaces, such as plastic or rubber. This can create a spark hazard, especially in environments where flammable materials are present. Grounding non-conductive surfaces can help to dissipate static electricity, reducing the risk of sparks. Static grounding straps and other devices are available for this purpose. In hazardous locations, such as areas where flammable gases or dusts are present, special grounding requirements apply. These requirements are intended to prevent sparks and other ignition sources. Equipment used in hazardous locations must be specifically rated for the environment and must be properly grounded and bonded. Lightning protection systems are designed to protect buildings and equipment from lightning strikes. A lightning protection system consists of air terminals, stand conductors, and a grounding system. The air terminals intercept lightning strikes and provide a path for the current to flow to ground. The down conductors carry the current from the air terminals to the grounding system. The grounding system dissipates the current into the earth. A properly designed and installed lightning protection system can significantly reduce the risk of damage from lightning strikes. Telecommunications equipment, such as phone systems and data networks, is particularly sensitive to grounding issues. Ground loops and voltage differences can cause noise and interference, disrupting communications. Proper grounding and bonding are essential for ensuring the reliable operation of telecommunications equipment. The National Electrical Code provides specific requirements for grounding telecommunications systems. It is important to consult these requirements when designing and installing telecommunications equipment. Medical equipment also has stringent grounding requirements due to the sensitive nature of patient care. Improper grounding can create a risk of electric shock to patients. Hospitals and other healthcare facilities must adhere to strict grounding standards to ensure patient safety. Regular testing and maintenance of grounding systems in healthcare facilities are essential. Data centers are another type of facility with critical grounding requirements. Data centers house sensitive electronic equipment that is vulnerable to power disturbances. A well-designed grounding system is essential for ensuring the reliable operation of data center equipment. Grounding and bonding are crucial for preventing electromagnetic interference, or EMI. Electromagnetic interference can disrupt the operation of electronic equipment. A well-designed grounding system can minimize EMI by providing a low impedance path for unwanted currents to flow to ground. Shielded cables and other EMI mitigation techniques can also be used. The grounding system should be designed to minimize ground loops. Ground loops occur when there are multiple paths to ground, creating unwanted currents. Ground loops can cause noise and interference in electronic equipment. Proper grounding and bonding techniques can help to prevent ground loops. The grounding system should be designed to provide a low impedance path for high-frequency currents. High-frequency currents can be generated by switching power supplies and other electronic equipment. A low-impedance grounding system will help to minimize noise and interference caused by these currents. The grounding system should be designed to be robust and reliable. The grounding electrodes and conductors should be sized to handle the expected fault currents. The connections should be made using approved connectors and fittings. The grounding system should be inspected and tested regularly to ensure that it is functioning properly. The grounding system should be designed to be compatible with other electrical systems in the building. The grounding system should not interfere with the operation of other electrical systems. The grounding system should be designed to meet all applicable codes and standards. The National Electrical Code provides detailed requirements for grounding electrical systems. It is important to follow these requirements carefully to ensure that the grounding system is safe and effective. In addition to the National Electrical Code, there may be local codes and standards that apply to grounding systems. It is important to check with the local authorities to determine what requirements apply. A well-designed and properly installed grounding system is an essential part of any electrical system. A properly grounded electrical system will help to protect people and equipment from electrical hazards. Proper grounding and bonding are not just a matter of code compliance. They are essential for safety and reliability. Do not take shortcuts or cut corners when it comes to grounding and bonding. A properly grounded and bonded electrical system will provide years of safe and reliable service.